Hello and welcome back to orgochemworld. Today I'm going to talk a little bit about some of the types of intermolecular forces that you'll encounter in organic chemistry. Today we're going to start off with van der Waals forces, and I moved away from the paint videos because they were just horrible and it was very pixely, and I found this cool program called Smooth Draw, and it's free. And I like free things, so there we go. Alright, so first of all, we're going to start off with our weakest of all the intermolecular forces, and those are the van der Waals forces. Okay, and these forces are basically in any organic molecule. What happens, what causes these are just momentary changes in the electron cloud density. So let's say you have a CH3, CH2, CH3. What this is essentially saying is that the electron cloud can get bigger in some places at certain times, and you can create momentary dipoles in the molecules. And what that means is that you'll get these slight charges, and say you have another molecule that is doing an opposite charge at the same exact time, and you happen to get some attraction that way. And the thing is, they change all the time, so you have no idea what you're going to get, and it's just like the least of all the intermolecular forces. Okay. Next, we're going to talk about some of the sorry, still getting used to the new program. But next, we're going to talk about the second highest, which would be the dipole-dipole. Anything that has a net dipole is going to fall in this range. Okay, so say we have something like water. We'll do water. We have an O there, and we have our two H's. Now the oxygen is more electronegative, which means that there's going to be a net dipole moment here. And so when you can tell that there is a net dipole is when you stack these arrows on top of one another, and they continue, and they don't like cancel each other out. So you can stack these on one another and they won't cancel out. However, if you have a molecule where the one arrow maybe points down like that, and then you have another arrow that points up, obviously those will cancel out, and it won't be a dipole moment. They'll just be a stabilized molecule. But as you can see on this, you have a net dipole. Next, we have hydrogen bonding. We can characterize hydrogen bonding in the same way sort of that we did with the dipole moments. Now we have already established that this is going to have a overall partial negative, and this will have a partial positive. Now hydrogen bonding exists whenever any of the halogens have an H attached to them. So like oxygen, nitrogen, or fluorine, those will all be able to do H bonding. And what I mean by H bonding is that you have these permanent dipoles set up, and you have maybe another molecule that is stacked on there. Well, these two are going to be attracted very strongly to one another because of their charge. The reason why you have such a strong negative charge here is because of the lone pairs that are still located there, and the oxygen is so electronegative that it's pulling most of this electron cloud away from the hydrogen, which is giving this a pretty strong positive charge. So hydrogen bonding is one of the stronger intermolecular forces. However, hydrogen bonding doesn't come anywhere near to the strength of covalent bonding, which is just the sharing of electrons with two different atoms. Okay, so now we're going to talk a little bit about the boiling point in liquids with these intermolecular or not liquids, but in substances with these different molecules that have these intermolecular forces. Now, just kind of intuitively speaking, the stronger the intermolecular forces, the harder it is going to be to break the molecules apart. So you have something that's like this, and it's not very strongly attracted to something like that. It's going to be much easier to split these apart and get the system excited and get a bunch of different interactions going on. But if you have something that's very attracted to one another, so you have maybe something super glued to something else, and you try shaking it like no other, you're not going to be able to split it apart very easily. So this is definitely where it comes into play. So we'll just start off with a couple of examples, and first we're going to start off with just a pentane molecule. 1, 2, 3, 4, 5, 6, 7. Actually, heptane, not a pentane. Pentane, or yeah, heptane. Oops. Yeah. CHO, and then OH. Okay, now we're gonna kind of explain why one is better than another. Okay, so if you have a cup full of each one of these three, which one would you expect to have the lowest boiling point? Well, if you think about it, the one that has the least intermolecular attractions are going to have the lower boiling point. So if we look at this heptane molecule, and we can realize first off that if you had another one stacked on top of it, the only forces that are going to be attracting it at all are the intermolecular forces, and or the van der Waals forces, also known as London forces. Now those are the weakest, which is going to make the boiling point the very lowest. So we'll go ahead and mark this 3 for the very lowest. Alright, now we're going to look at this molecule. I'm going to go ahead and just draw this a little differently so you get the point I'm trying to make here, so you don't get confused. Okay, now this looks like it's going to be a really strong, possibly stronger than anything else we have here, as far as intermolecular forces go. However, this doesn't have H bonding, so if you can see, this oxygen is directly connected to this carbon. So what's going to happen is that we will get a permanent dipole, and the moment's going to look like that, with a positive charge going this way and the negative over here at this oxygen. Okay, and so this is going to be the second highest. And first we have this heptanol, which it has H bonding, so it's going to be the highest, and so that means that this hydrogen has a overall positive charge, and then on an oxygen of another molecule we have an overall negative charge, and so these will be attracted very greatly. So the boiling point will be much higher on this one. Alright guys, probably do a couple other examples before moving on from this, and I'll talk to you later. Bye.